So indeed, I'm going to talk about the boundary crossing problem for the Brown motion. And so let me start explaining the title. So it will be a two-step process. So I will first explain the first line and then the second line. So our setup is very simple and the problem is very easy to describe. We simply consider a Brown motion defined on a filtering probability space and a function f, okay, defined on R plus, and we are interested about this stopping time Tf, which is the first time the Brown motion will hit the moving boundary, the curve f. So this is so we have a Brownian path here. Okay, and we have a curve f here. So throw introductory ft and here. And we're interested about getting information about the random variable tf. So the question is, what is the distribution of the stopping time tf? For which type of curve we can get some information about this distribution. So beyond its probabilistic interest, so this problem has attracted the interest of many research. So in particular, in statistics, so people realize that the law of the iterated logarithm, which is due to Khinchin, has some meaning in statistics, and the design test for detecting in a sample whether there is a trend. And it turns out that these tests are based on a distribution of the first passage time of Brown motion to a curve. Then there is a close connection. So each time we are talking about Brown motion, there is his best friend around him, and his best friend is a heat equation. So there is always a connection between a problem related to the Brown motion and the heat equation. So I will discuss further about this connection later in this talk. Then there is also connection with spatial function and spectral theory for being able to describe the distribution of this stopping time. And so in mathematical finance, also this distribution plays a key role in the pricing of path-dependent options and American options. So in American options, it turns out that the optimal time at which a buyer should exercise his right corresponds to the first passage time in the Black-Scholes model of the Brown motion to some moving boundaries. So, but the curve in this case, to satisfy some integral equation, we are not able to get an explicit representation of this curve. Then there are many fields where this problem occurs. So I mentioned a few of them here. I would just like to mention that in neurology, there is an open problem which leads to a very interesting theoretical problem. So one of the concerns in neurology is to understand how the information is transmitted, the information is transmitted within the neuronal system. And when you look at a single neuron, so there is an analytical mechanism, and it turns out that the information from one neuron to another one is transmitted as soon as the potential within one neuron reaches a certain threshold. And the input signal in the model which are suggested in this area are periodic time-dependent signals. And the question is to understand, the time at which the neuron will transmit the information corresponds to the first passage time of the dynamics to a fixed level. And you can transform this problem into the first passage time of Brown motion to some moving boundaries. And the question is to understand how this period affects the distribution of the first passage time of the model to the boundary. And there is no answer to that. So in some sense, we want to know if the distribution is multimodal and the mode are related, if there is connection between the mode and the periodicity of the input signal. So then I mentioned a few names, and the list is not exhaustive about people who has worked on this topic. So I will come back to most of them later during this talk. So next, I'm going to give some general results about this problem. So the first one is about the smoothness property of this distribution. So it's due to Strassen. If the curve f is C1, continuously differentiable, then the distribution is absolutely continuous with a continuous density. Okay. Then we have a result related to the transients of f, so which is due to Kolmogorov, Erdos, and Kretowski. So if f is a positive increasing function, such that the ft over the square root of t is also increasing for large t, then the distribution is defective, or it has a Dirac point mass at infinity if f satisfies this integral test at infinity. Okay, so some of you might recognize here for this integral test the density of first passage time of ground motion to a fixed point, and consider the fixed point is simply replaced by the boundary, moving boundary. Then we have an asymptotic result due to Novikov. So there is exponential decay of the tail of the distribution. So if we consider a function f which is continuous, starting from a negative point, and such that for large t is f second is continuous, increasing and concave, and satisfy this asymptotic behavior at infinity, then we have an exponential decay of the tail of the distribution, which is given in the log scale by this expression. So the type of curve which satisfy Novikov condition are this. So we start from 0, is increasing. So I'm not sure about. So it's convex, this one. So you have what is behind that is that you will cross quickly the trajectory of the Brown motion, which makes the exponential decay of the distribution. And another type of asymptotic result is due to Ushiyama. So if function f is continuous and starting from f0 is positive, and satisfy this integral test again at infinity, then we have the tail of the distribution of Ts which satisfy this asymptotic behavior, and this symbol simply means that asymptotically the tail of the distribution is bounded from above and below by a constant times 1 over the square root of t. Okay, so that's is not all results about this topic, because there are a huge amount of results related to this problem, but that's probably among the most important ones. So now I will turn to the explanation of the second part of the title. So just before going there, I would like to say that it will be the last time in this talk that you will see inequality, okay, and the sign equal. So why? Because the calculator viewpoint is explained. So I'm quoting Mark Cox, who was a professor at Cornell some time ago, and who says that mathematicians, or rather mathematical analysts, are divided, roughly speaking, into two classes. So the calculators, that is those who look for exact formulas, and the estimators, that is those who live by inequalities. And so he said that he belongs to the first class. Okay, so that's the reason why I will, the title about the calculator viewpoint, I will be focusing only on exact formula. So you will see only the equal sign throughout the rest of the talk. So what I'm going to do is to present the methodology which have been designed for getting explicit representation of this distribution for specific curves. Okay, and there will be 4 of them. So the first one is the most natural one. So it's a Biersenhoff approach. So for that, we consider a function f, which is C2, and we consider the process Bf, which is simply Bt minus Ft. So it is obvious that the first passage time of Bt to the curve f corresponds to the first passage time of 0 of this non-homogeneous process. Then, by Cameron-Martin theorem, we know that the law of Bf is absolutely continuous with respect to the law of the Brownian motion. It's absolutely continuous with respect to the Wiener measure. So the fact that f is C2 is not a necessary and sufficient condition. It's just a sufficient condition. F can be in the so-called Dirichlet space for having the absolute continuity. So now, what does it mean? It means that if I'm writing, so the law of Bf, so there exists a Martingale, and the Martingale is given by, so it's an exponential Martingale. Yes. So here I have the law of the Brownian motion starting at x, okay, and here the law of Bf starting at x, and I have this Martingale here, okay? And the trick is simply to use integration by part. So I print x. Okay, I'm simply using integration by part for this expression here, because the calculator does not like this, this type of term. Okay, so a calculator will always try to find a way to get rid of this type of term. So the trick is simply to use integration by part, so auto formula if you prefer. And what you do, you replace this term by the other term involved in this identity. Okay? And then you do that, you just apply the optional stopping theorem, and you end up to this segment which is due to Salmin n. So if you have a function which is C2 starting at 0, then you have the distribution of TF, so the distribution of TF, which is expressed in terms of the distribution of the Brownian motion to the level 0, okay, and some terms here. So these terms are explicit, and it just remains, so this term will correspond to exactly this quantity here, okay, condition on the fact that T0 is at T. And and we have an explicit expression to the passage time at 0 for the Brownian motion. So from a calculator viewpoint, for which kind of curve do you think that this DSNF approach is useful? So a calculator always seeks for explicit representation. So there is a curve for which it is obvious. So what we don't like here, so this term is explicit, this term is also explicit.
Second order is 0?
Yes, okay. So when f second is 0, so which give us the passage time of Brownian motion to a linear boundary, okay, for a curve of the form AT plus B. So
but in that formula, do you need this curve to be hittable or not? This formula, do you know something? What if the curve cannot be hitted? I mean, what's the the infinite T? Still true or NF?
Yeah, that's about the density. So what you have here, the curve. Yeah, what you will get a concern with this term here. Okay. You will have that's this term will tell us about
Yeah, about if the curve can be reached or not.
The density will not be
Oh, all right. So may not be.
Yeah.
Okay. Yeah.
Yeah.
Is this the form
Yeah, it can
one?
be defective, of course. And so another thing that the calculator does not like is non-homogeneous problem. Okay, calculator does not like to deal with time-dependent problem. So there is another curve which can be of some interest here. So the linear one, we will get rid of this term. Okay, what we don't like, a calculator does not like the fact that there is this functional of the Brown motion involving non-homogeneous term, which is time-dependent. But if you consider the quadratic curve, okay, then you will have something homogeneous. So the Gersonov approach has allowed to get explicit representation for the boundary crossing of linear curve and the quadratic one. So I just mentioned two remarks. So we have the expression here up there. Then what you can do is to use Williams time reversal formula, which states that a Brown motion, if you reverse the trajectory of a Brown motion starting from a positive level up to the heating time of 0, if you look at the trajectory in a reverse way, this corresponds to the trajectory of a three-dimensional Bessel process killed at the last exit time of the level x. Okay, the transient process. And what you can do is by using this time reversal argument, transform this functional involving the Brown motion into the functional involving the three-dimensional Bessel bridge over the time interval 0t, starting at x and ending at time t at the level 0. Okay? But unfortunately, this type of transformation is not very useful for a calculator, but it might be useful for an approximator, I would say, because you can use a Monte Carlo method to get an approximation of this functional. And as I said earlier, so the Gersonov approach allows to get an explicit expression, so a very simple one for the first passage time of a Brown motion to a linear curve, which is the so-called Bachelier-Levy formula. So just to mention that this problem dates back to the 1900. Bachelier in his thesis derived the first passage time of Brown motion to a fixed level. So this problem is pretty old. And then concerning the quadratic curve, so it's due to Cronenboom. And the density of this first passage time can be expressed in terms of as a series representation which involves the zeros of the so-called Airy function. I will come back to that later. So that's the first approach. So then there is a second one. And always the idea is to find some devices to get rid of the non-homogeneity property of the problem. So there is another approach which involves the so-called Gauss-Markov processes. So we define them like that. So we have x, we have a phi, a positive and continuous function, and then we define x in such a way. So x is phi t, and the integral respect to the Brown motion of 1 over phi. So that's a Markov process, and which anytime t has a Gaussian distribution. So it's a Gauss Markov process. And why this process are interesting? So if we are looking at the first passage time of this non-homogeneous process to a fixed level. So now, so we started from a homogeneous process, the Brown motion hitting a non-homogeneous level, and now we transfer the problem, so we have a non-homogeneous process which hits a fixed level. And why there is a connection between these two problems is h of phi So it's simply what you can do is use Dubin's-Damin-Schwarz theorem, which says that here you have a Gaussian martingale. Its stochastic integral is a martingale, and it can be written down as a Brown motion, another Brown motion, time changed by the quadratic variation of this integral. So So it is this Brown motion time change by the quadratic variation, which takes this form here. And so what we get is that so I'm considering rho phi, which is the inverse of tau phi. Okay, and I'm just setting so okay, I have so by time change, then that's a simple trick, and then I'm taking the inverse of this functional here, and what I obtain is that h of phi is simply rho of phi of, and this passage time corresponds to the first passage time of Brown motion to the curve ft, where ft is 1 over this expression here. Okay, and what is nice here is that this function is a deterministic function. So we have a simple relationship between the heating time of a fixed level of our Gauss-Markov process and the heating time of the Brown motion to a fixed level. Okay, so having said that, now the natural question for a calculator is to find a condition under which this guy is a homogeneous process, because I will have a homogeneous process hitting a fixed level, and it turns out that among this family of Gauss-Markov processes, there is one which leads to diffusion, so homogeneous process. So if you consider phi to be the exponential of minus t over 2, then x is simply the classical Orschen-Lembeck process of parameter 1/2. Okay, so x in this case is linear diffusion, so it's a homogeneous Markov process. And what you can do, so if we compute here this quantity, so you will end up to tau phi t, which is so exponential t minus 1. Okay, I'm simply replacing the term. So rho phi of t is log of t plus 1. And you will get that ft here is a square root boundary. Okay, so we obtain this result. So Brayman find the Laplace transform of first heating time of the Brown motion to a fixed, of the Orschen-Lembeck to a fixed level, and Shep realized that there was this connection between this boundary crossing problem for the Orschen-Lembeck process and the boundary crossing problem for the Brown motion. So what we have is this almost sure identity between the two stopping times, and what we obtain is that the Mellin transform of the first passage time of the Brown motion to the square root boundary can be expressed in terms of the ratio of the so-called Hermite function. So that simply means that the Laplace transform, so by this transformation, the Laplace transform of the first passage time of the Orschen-Lembeck to a fixed level is expressed in terms of this Hermite function. Okay? So now, the reason for why we have this connection between this Orschen-Lembeck and the square root boundary, so it's due to the scaling property of the Brown motion. And there are two reasons for that. So the first one is by this time change, the fact that we take for phi t the exponential function, and the scaling property of the Brown motion shows that this process is homogeneous Markov process. So for showing that the Orschen-Lembeck is a homogeneous Markov process, when you represent it in such a way, okay, the scaling property plays a key role. So that there is one explanation why we have why the square root boundary, the expression for is Mellin transform is accessible is because of the scaling property. And there is a second reason, which I will describe now. So I will just give a very general proof of this relationship between why you can get the heating time, the expression of the or characterization of the distribution of the heating time of the square root boundary for the Brownian. And I will provide a proof for all self-similar Markov processes. So I leave you some time to understand the first, because notation are unusual here. So what I'm considering is a Feller semi-group. Okay, so the semi-group associated to a Markov process which satisfy the 1/2 self-similarity property. So we could choose any index of self-similarity. Everywhere you will see the square root, you have to replace by 1/alpha, and alpha is the index of stability. And to explain the first, what I mean by the self-similarity property, so what I have, so a semi-group is simply, so my third example will be through this part of the Brownian. So a semi-group is simply defined like that. It's just the expectation where you have the starting point here, x. And so what is the meaning of that? So the scaling property, what I'm doing here, I just, okay, so it's perfect. So that corresponds to DC composed with F, where DC is a dilation operator. Okay, that's just a notation. And this one, by the scaling property, corresponds to so the expectation of the Brownian starting from the square root of Cx of F dct. Okay, and which is in terms of the semi-group this expression. Okay, so just and this scaling, the usual scaling property is expressed here. Okay, when you have a scaling of time, which is equivalent to a scaling of space. So next, I'm introducing another so well-known object in potential theory. So it's a so-called R invariant function. So I'm considering a non-negative Borel function which satisfies this identity. Okay, so why this type of function are interesting is because they generate Martingale. So what you have is that, so if I of R is an R invariant function, then the process exponential minus RT, I R, so of dt, so this one is a Martingale. Okay, and that's very useful for getting expression for the Laplace transform of passage time, because then you apply the optional stopping theorem to this type of Martingale. So if you have monotonicity, you can use dominated convergence, and then you can easily derive the Laplace transform of passage time of the process. And why it is a Martingale? So that's simply now. So E of RT so PT plus S minus S. So I'm just shifting. So minus S plus S. Okay, Fs, and I'm using the Markov property, and this quantity is simply E of Bs of ER Pt minus S. Okay, that's a straightforward application of the Markov property, and then this quantity is simply, by definition of the semi-group, Pt of IR Bs. Okay, and now I'm using the fact that this function is R invariant. Okay, function is R invariant, so exponential minus RT, and I will have exponential of R T minus S. Okay, I'm using it's just the exponential term on the other side, and R B of S. Okay, which give me so the Martingale property. Okay, so there is equivalence between so this I would say analytical formulation and Martingale's. Okay, so now from the self-similarity property, you play with this expression, and what is interesting for self-similar Markov process is that if you know the one invariant function, so for R is 1, then you get easily the R invariant function. And the R invariant function are simply given in terms of the one invariant by the scaling of the space variable. Okay, so in the case of the Brown motion, what you have so for the Brown motion you have so the Martingale associated to the Brown motion is I will write like that. So 2R square root of 2R BT. Okay, this is the Martingale, and the function so E1 of x so is exponential square root of 2x, and you get that E1 so ER in this case. So I'm just getting x by the square root of R. So if you can read. Okay, so for the Brown motion, this guy is a Martingale, and you switch from the one invariant to the R invariant by just the scaling of this factor. So now, we have this result. So I mentioned several names is because, so as I said earlier, for the Brown motion, okay, I will state the result and explain what's going on. So what I get is that, so I'm considering now a gamma random variable of some parameter q positive. I assume that the one invariant function is L1 of respect to the density of the square root of this gamma. And then I construct a function iq of x, which is simply the image of my function I, the one invariant, respect to the multiplicative kernel associated to the square root of a gamma random variable. Okay, there is a simple expression, I will mention it later. And it turns out that this function iq is a time-space invariant function in the sense that it satisfies this identity here. Okay, so what is the meaning of that? So the self-similarity property allows to transform this type of invariant function into this type of time-space invariant function. So if I mention several names here, it's because so Shep use this device. So in the case of Brown motion, and prove it by hand. So he proves that this object is a Martingale. Okay. Then Markov extended the work of Shep for Bessel processes, and also provide a proof. He proves that the equivalent object is a Martingale by length. And actually, what I'm going to show here in 2 lines, that using the semi-group theory is straightforward to get this property for very general Markov processes, because we cannot prove, we don't have access to Martingale in general for self-similar Markov processes, but we still have this connection between these invariant functions. So what we have is that, so I'm simply, so the space of invariant function is stable by, is a cone, so I can multiply to make the notation simpler by any constant. So the meaning of this notation is simply that, so it's given by this expression here, where I have the density of the gamma random variable. Okay, so just a simple transform. And now to prove this identity, so I'm starting from the left-hand side, then I'm simply using, so everything is positive Fubini theorem. Okay, and then what I'm using from here to here is the fact that the function I is invariant for Pt, okay, and the parameter is given by the dilatation, the parameter of the dilatation operator, so which gives me this expression here. Okay, the invariance of I gives me this expression, and here is the fact that so this function is R over 1 plus T invariant. Okay, and then I'm simply using change of variable, which is expressed here, and I'm going back to this function IQ. Okay, so what I obtain is 1 plus T minus Q times this term is IQ. Okay, which was the statement. So what you can do, the conclusion here is as soon as you have you derive the first passage time to a fixed level for a self-similar Markov process, you can derive the Mullen transform of the first passage time to this type, so the square root boundary for the 1/2 self-similar, or a boundary to raise to the power 1 over alpha, the index of self-similarity. Okay, so then we have another approach. So as I said, there is a close connection between a problem related to the ground motion and the heat equation. And so the relationship between our problem and the heat equation is given by this proposition, which you can find in a book of Lerch. So I'm assuming to do not have to deal with the issue of existence and uniqueness of the solution of this heat equation. So I'm assuming now that the function f is very smooth. Okay, and so I'm considering now the solution to this boundary value problem, where so you have the heat equation, okay, which is in the domain df, and the domain is given by the boundary, the moving boundary f. Okay, then I have this boundary condition. So at when x, y is ft, so we have the Dirichlet condition is absorbed there, and we have this initial condition at time 0, with the Dirac bound mass at 0. And so since we have a unique strong solution, you can use Ito's formula, and you can show that actually the solution of this boundary value problem has a probabilistic interpretation, which is simply the transition probability of the Brown motion killed when he hits this boundary. Okay, and then integrating this term respect to the space variable and differentiating respect to t, what you obtain is that the density of the first passage time, so which I will denote by pft, so the law of tf in this case is continuous with the density given by denoted by pft, and which is simply minus 1/2 of the partial derivative of the solution of this boundary value problem considered at the point ft. Okay, so if you solve this PDE, you can get an explicit expression for this density, but it turns out that we don't know how to solve this PDE. Okay, except for the linear boundary, there is no easy ways of computing, of solving this PDE. However, there have been a methodology, so the so-called method of images, which has been suggested to solve this PDE in a certain way, and I'm going to describe it now. So we consider a measure mu, okay, a positive sigma finite measure mu, which satisfies the integrability condition stated up there. So the integrand is simply the Gaussian density. And we define the function h as follows. So it is the difference simply of the Gaussian kernel, okay, minus, so the Gaussian kernel integrated with respect to this positive measure. So it turns out that, so it's a result from Wieder that all positive solution of the heat equation admits this representation. So it's simply, you take the elementary solution, which is the transition density of Brownian motion, and you integrate them with respect to a positive measure, and they will, if the measure satisfies this integrability condition, then this function will be also a solution of the heat equation. So you just need to plug in this function into the heat equation. It's just a matter of being able of switching the differential operators and the integral sign. Okay? But it's obvious, because this term will be 0. And so what we get is that, so the heat equation is a linear equation, and we have the linear combination of two solutions, so this function h will be also a solution of this heat equation. Okay? And then, so to this function h, we can associate, so the unique root of the equation, so for a fixed t, of hy t. Okay, so you are looking for a function f, which is solution of h of ft t is 0. Okay, in the space variable. So what happens here, what you are looking for actually is simply, what you can think about is that this term corresponds to the transition density of a Brownian motion starting at 0. So with the initial distribution, the Dirac mass at 0. And if mu is a finite measure, what you can think about this term is the transition density of a Brownian motion with initial law mu. Okay? And this curve f, how do you obtain the curve f? It's simply by plotting at any time t the transition density of this guy, of the Brownian motion starting from 0, and the transition density of this one with initial law mu, and they will intercept at some point, okay, and that will be the corresponding point of the function f at this time t. You fix t, okay, it's simply, just by definition, you need this quantity to be 0. So that will be at for fixed time t when these two functions intercept. Okay? So, from that, what you can do is to simply use so the previous expression down there, and you get an explicit representation for the density of the first passage time to f, which is expressed in terms of the measure mu. Okay, simply differentiating h in a proper way. So the drawback of this approach, is that you start from a measure and then you describe the function f. And it might happen that for some problem you have a function f and you want to find the distribution. Okay, it's looking the problem in the reverse way. And there is an implicit function theorem behind this statement for the uniqueness of the root of this equation, and this implies that the function f should be convex infinity, and f over t should be monotone decreasing. So I'm just providing you some example of curve that you can obtain from this method. So if you start from, so the measure mu here to be the sum of two Dirac point mass at 1 and 2, okay? What you will obtain, so you can solve this implicit equation, and you will obtain this curve here, ft, and then it's easy matter to get the density. Then you can consider for this measure mu, a measure which is absolutely continuous with respect to the Lebesgue measure, and you will obtain the curve log t. Okay. So once again, you can obtain, by playing with this type of measure, you can obtain some example of curve for which we have an explicit representation for the density. So now I'm turning to the last transformation. So, so we consider transformation with two parameters, alpha and beta. So we have two real numbers, and to a function f, we associate the image of f by this transformation s alpha beta, which takes this form here. So you have a linear function times f, and f is considered as this argument here, okay, which is alpha squared t over 1 plus alpha beta t. So this transformation is defined for all t lower than zeta, which makes this expression finite. Okay, so what we obtain with Larby, so in a series of papers, what we show is that if you know the density, so I'm setting it for a function which is C1, we have a general result for any distribution. But if we have a density, so if you know the first passage time of a Brown motion to a specific curve f, okay, let's say that we have access to this density, what you can get is an explicit representation for the first passage time of the Brown motion to the image of f through this transform S alpha beta. Okay, and the relationship between this density are rather simple. So here is simply the image of the density with respect to this operator here. And then we have this term which looks like it has some similarity with the heat kernel. Okay, taken at S alpha beta f. So let me give you some example of curves that we can study now. So the image of affine function is an affine function. So it's almost invariant. So there is one thing I should say now, is that, so actually we prove this statement so in a different ways. And one of the key property we use through one proof is a so-called time inversion property of the Brown motion. So we say that, so we have t b 1 over t has the same distribution than dt. Okay, the time inversion property. And it turns out that that's a key property. So we can generalize this result for all processes, Markov processes having this property. And it turns out that the Bessel process have also this property. So we have this type of relationship for Bessel processes. And if I'm saying that, it's because if you take here p is 0, okay, so just a constant. So if you have the heating time of a constant, this transformation allows us to get the heating time of a linear curve. And for Bessel processes, it was an open problem, how to get the distribution of the Bessel process to a fine function. And so then for the square root boundary, we have the square root of a polynomial of order 2. And for the quadratic curve, so we have the ratio of a quadratic function against a fine function. So in particular here, if you play with the parameter, you can make this coefficient here 0. And what you obtain is 1 over an affine function. And so using the result of Cronenboom, who derive an expression for the density of first passage time to the quadratic curve, then we get that the density of the first passage time of 1 over a affine function admits this series of representation. So I will not go into details, but what we have here is the so-called Airy function, and that's 0, the sequence of 0. Okay, so to derive such expression, so one uses spectral theory associated to some differential operator to which the Airy function is solution. Then there is a connection so with a theory of images. So if you remember here, if we start with the measure mu, we can associate a function f, and we have the density. So the question is, what is the measure mu associated to, if I start from a couple mu f, if I transform f with our transform S alpha beta, what is the associated measure mu? And there is a simple transformation So the measure mu beta, which is associated to the transform of f, can be expressed in terms of mu with a Gaussian density in front. Okay, so how much time do I have? You said 1 hour?
5 minutes.
5 minutes? So, okay. So what I'm going, so I will maybe skip this proof. So here, what I've used here is just the connection. So the idea is that, if you remember, so we have a connection between h5, so the heating time of a fixed level of this Gauss Markov process, and tau f. Okay, we have a certain. So h5 was phi t. So h5 was the heating time of 1 of the Gauss Markov, and we have this relationship. So the idea here is simply to say, okay, I start from f, I associate phi, okay, so Gauss Markov, so at Tf I make a link with h of phi, okay, and there, so the link is obvious, so it's given here, we have an explicit representation between the heating times, and then here we introduce a mapping which relates, so two Gauss Markov processes, so one associated to phi, and the other one associated to the image of phi with the two parameters of transformation. And these two parameters of transformation describe the set of solutions of certain Sturm-Liouville equation. Okay? So in some sense, we have two Gauss Markov process where the covariant function are related respect to a certain parameter, and what is very interesting is that their laws are absolutely continuous, and what a calculator like is when the Martingale does not depend on the trajectory of the process, but only on the terminal time. Okay? And what we have is that the Martingale here, linking the law of these two Gauss Markov process, depends only on the terminal time. So here you can think about bt or xt. It depends only on the terminal time of the process. And why it is interesting is because you can use the optional stopping theorem and you get explicit representation. So that's so-called double-H transform, when the Martingale depends only on the terminal time. And then, so we have a relationship between, so here, h phi, and then I associate p alpha, beta phi, okay, and the trick is simply to come back to f. Okay, from f we move to phi to this guy. We have explicit relationship between heating times, and then I'm coming back to f. Okay, and I will get S alpha beta. So, which is this third slide. Then, so I'm going also very fast here, just to say that it's the relationship, why the time inversion property is playing a key role, is because if you consider the bridge, the standard Brown bridge, then its realization can be expressed as a time change of a Brown motion. So it takes this time-space transformation, and this time-space transformation is possible due to the time inversion property. Okay, to make, you simply compute the transition density of the two guys, and the time inversion property is being a key role. So then the idea is that you have also a calculator Martingale linking the law of a Brown bridge with the law of the Brown motion itself. And when I'm saying a calculator Martingale, it's because this Martingale depends only on the terminal value of the process, not on the trajectory. Okay? And then you can play with these two guys and you will get our relation. And I would like just to spend 2 minutes on this third proof of this fact, which involves some algebraic techniques. The idea is there. So what we are looking for is solution of the heat equation. Okay, so this equation. So there is this equation, of course, has been intensively studied, and in particular, so Lee suggested some algebraic methodology to solve this equation. So his idea is to discover some symmetry. So the symmetry are just one parameter group of transformation which leaves invariant the space of solution of this heat equation. So you start with one solution, and you can apply a transformation to this solution, which makes the transform function also a solution. That's the idea of Lee. So, so there is a deep theory behind that, and what he found, what is very nice, is that he has found with this approach, you can find all possible one group of transformation leaving invariant this, the space of solution. So, so you have this 7 transformation. So this one, you can think here about the transition density of a Brown motion. What I'm doing here is just a shift in space, a translation. And we know that the Brown motion, the law is invariant by translation. But time translation, the law is also invariant. Then here, if you combine these 2 groups of transformations, then you will end up to the scaling property. Okay? Here, this one is simply the transformation between the law of a Brown motion and the law of a Brown motion with drift. The calculator Martingale again, which depends only on the terminal value. Okay, so this one, here, all these guys, if this one is solution, this guy is also a solution, that's the idea. And the last one, so this one is called the Galilei transform, this one the Apple transform. This one just simply relates, so the law of the Brown motion with its bridge. Okay. And the last one is simply the fact that we are dealing with a linear equation, so you can take 2 solutions and they will remain a solution. Okay, so this one you can think about taking 2 independent Brown motions. So what is very nice behind that is that there is unique, we have a complete group of transformation here. And if a student asks you at some courses, you will describe all properties of the Brown motion, does there exist any other transform which makes the law of the Brown motion invariant? And from a probabilistic point of view, it's not very easy to answer to this question. What Lee is saying here is that there does not exist such a transformation. Okay, because all this type, which generate a group, okay, so is what is telling Lee is telling us. Okay, so the link now between this problem and our problem is the fact if I combine this 3 group of transformations. So this one, as I said, is a scaling property. This one is a Brown bridge. So behind that there is a time inversion property. And if I combine them in a proper way, so I can define a 2-parameter transformation, which will, so once again, if H here is a solution, so this one will be a solution. And so the problem of Lee approach, it does not tell you how you transform a boundary value problem. So it's simply about the equation itself, not about the boundary conditions. So what we obtain here is that if we have H, which is solution to our boundary value problem, so with a domain which depends on the curve F, then this transform here will be solution of the boundary value problem associated to the transform of F by our transformation as alpha beta. Okay, and then you can get the proof by linking, by the expression down, okay, between the solution of this boundary value problem and the density. So I will just complete, I think I still have 30 seconds. 1 minute?
No, 0, -1.
Okay, just some open questions. Just some open question. So what Lee techniques also allows to get usually is the invariant solution, in the sense that if you have some function which are invariant under this transformation, then usually his techniques allows to get the solution of the associated heat equation. And here we have a problem, an interesting problem, is that if you consider the curve f beta t, which is t times capital F beta taken at 1 over t, where capital F beta is a periodic function. Okay, so these functions are invariant under our transformation. So what our expression says that the density of this of the passage time to this curve should satisfy so what happens is that on the right and left hand side we have the same object. Okay, and can we solve this functional equation? And it turns out that we can get the expression, the problem is about uniqueness of the solution of this functional equation. And then the last question is about getting, so since the time inversion property plays an important role in our result, so there is an open question, is to describe the class of Markov processes which enjoy the time inversion property, which means that if I make this transform of the process, it will remain a homogeneous Markov process. So this transform always leads to a Markov process which is non-homogeneous, and there is an open question about characterizing the class of Markov process which remain homogeneous under this type of transformation. So I just mentioned that Watanabe characterized completely the class of diffusion, satisfying so is the Brown motion and the Bessel process. And Gallardo and York provide a sufficient condition in terms of the transition densities, but the problem is that you can get only one additional, the so-called Dunkel processes, one additional example. And just to say something is that, so what one can think about using Lie group techniques for getting, because the Lie group approach should be able to provide us, in the Brown case, this time inversion property. But the thing is that if you go beyond the diffusion world, you are dealing with non-local operators, and Lie group techniques do not work for non-local operators. When you have an integral term, Lie approach does not work. Okay, so that's also very challenging from an algebraic point of view to find ways of dealing with this question. Okay, sorry for the...
Questions?
For the PDE solution, PDE equation, so you have given view, you have a solution, you can find corresponding f.
Yes.
Did you answer the question what about reverse? If you given f, do you always can find a view corresponding to that? Or
No.
No.
So what you need, the thing is that no, the way it is presented, you need to solve this implicit equation to characterize f. So you need to start from the function h in itself. So which means you need to start from u.
So but generally, start with f, there's no hope.
No, I mean, so f first of all has to satisfy this condition, but then there is no ways of going the reverse way, because f is characterized through this implicit equation. Yes?
Can you go back to Lie's list of transformations that preserve solutions of the equation?
So which transformation?
The one parameter family of
Please
sources.
observe this transformation.
Yes, the symmetry?
Yeah.
Yeah.
So, is there rotations should be there somewhere in this list, right?
Which one?
Rotations, the solution of heat equation is preserved by rotation.
But we are in a one-dimensional situation
Oh, I see.
here. Okay, so that's a scaling property.
So I guess, is there an analogous list for higher dimensions?
Yes. So actually, Lie algorithm is very powerful and it can deal with any type of partial differential equation of any order of any dimension. It does not mean that you can always figure out what are the symmetries, but at least there is an algorithm for dealing with any type of PDEs. Yeah.
In the previous list, you had one proposition where you could characterize PF by if f was C infinity.
Yes.
And then on the next slide, you showed that you can also do it if f is C1, but then you give examples that are trivially, this one, you give examples that are trivially C infinity anyway. So what's like a good example of something that's C1 that's not C infinity that you can give a sort of good closed form expression?
So we don't know actually.
Okay.
The thing is that, so the transformation, so here there are two things. Here, so what I meant, here we can start with any function, f, and I will mention this result in terms of the distribution, and which is not very elegant. So that's the reason why I stated this result with the function which are C1. And this result, so the second thing is that this result allows to connect the first passage time, you need to know already the first passage time to some boundary. Okay, and we don't know for, I don't have any example in mind of such type of density for functions which are only C1, if it is your question. Yeah, we don't know, I mean, beyond these three cases, and the one you can obtain from the method of images, they are usually a very smooth function.
Okay, so that's